Remember, the answer to this is 5 by 384 Q naught L raised to 4 by EI. We assumed it. We are now going to prove it. We are asked to find both the slope, maximum slope and the deflection. First step, what's the first step? Draw the bending moment diagram. Maybe for a beginner, you may have to first find the support reaction, shear forces, and then bending moment. But I would expect you to quickly get the bending moment diagram. It's parabolic, maximum value Q naught L squared by 8. Everybody knows this. It's positive. This you have to divide by EI and treat it as a distributed loading on your conjugate beam. What's your conjugate beam? Your primary beam, your main beam, your real beam is simply supported, so conjugate beam is also simply supported. And you have a distributed loading like this. The same diagram comes here. And find the total area of this parabola. Total area will be 2/3 the rectangle. Remember, actually it's two halves, you can join them together. 2/3 the rectangle. The rectangle is, the peak value is Q naught L squared by 8 EI. 2/3 of that into L, Q naught L cube by 12 EI. Half of that load will come here and here, and that straight away gives you a maximum slope. One shot. Very easy. So you got one answer. The two questions are, find the maximum slope, you got the answer, and find the maximum deflection. There are two different locations. Slope is maximum at the support, deflection is maximum at the midspan. Where the deflection is maximum, the slope is 0. Where the slope is maximum, the deflection is 0. Okay. So if you do this calculation, let's do it together. I've not drawn it here, but you should take the free body of one half, either left half or right half. Then this Q naught L cube by 24 EI into L by 2, we've done that. You can put your appropriate signs. And this area with an opposite direction, that area is 2/3 of the same, that area is nothing but half the total area, so you've already done that, into the distance of the centroid from the midspan. Remember, a parabola like this, the centroid will divide in the ratio 3:5. So 3 by 8 of L by 2. With some experience, you'll know how to do this. You can take the modulus of that. You can prove it's 5 by 3. So there are, remember, two ways of writing it. Either you write 5 by 384 WL cube by EI, or 5 by 384 Q naught L raised to 4 by EI, because W is equal to Q naught into L. That's it. Easy. Try this. This is a simply supported beam subjected to a concentrated moment at one end. Can you draw the deflected shape? You'll find that the slope at A will be more than the slope at B. And if you're very smart, let me ask you this question. Okay, let's see how smart you are. The slope at A and the slope at B, is there a relationship? Okay, you know the conjugate beam. You know that the slope is obtainable by loading the conjugate beam with the M by EI diagram. So you should know the variation of the M diagram. I'm not going to draw it. I want to see how many of you are very smart and quick thinkers. Then in your conjugate beam, you put the M by EI diagram, find the reactions at A and B, and those are nothing but the slopes at A and B. I just want the ratio, theta A versus theta B. Is there a ratio? So anybody can answer theta A versus theta B. Theta A will be more than theta B, but is there some ratio? Remember, you have a triangular bending moment diagram. That divided by EI is your curvature diagram, which you are putting on on the span as loading? Answer 2:1. Brilliant. JNTU, can we see your face? Brilliant. Okay, good answer. Perfect. Let's see. Okay. Very easy actually, because your reactions, your bending moment diagram will be like this, sagging, M naught. Your conjugate beam will be also simply supported, and the M by EI diagram will look like that, positive upward. Obviously, the centroid of this will divide this in the ratio 1:2. So the reaction on the left side will be 2 times the reaction on the right side. That's what makes this theta A. Remember this, it's a golden rule. But it is true only if the beam is simply supported, only if the beam is prismatic, and only if one moment alone is applied at one end. It will be always true. So whenever you draw this also, make sure that when you draw a tangent here, this slope is roughly 2 times this slope. Easy to remember. Okay, and we've got the value. We got one answer, M naught L by 3 EI, and the other one, if you want, is M naught L by 6 EI. Actually, this is a famous relationship. It's a stiffness relationship. If you replace the whole beam with a rotational spring, then the rotational stiffness of that spring is the ratio of the moment and the slope. And that stiffness turns out to be 3EI by L. Very famous relationship. Okay, so you got one answer. Now we are also, this is a tricky question. And this is not so easy to answer, because where is the maximum deflection? We don't know. If the question was find the deflection at midspan, easy. Just take 1/2 and quickly crack it. That anybody can do. Where is the maximum deflection? I don't know. I know it's somewhere in the left half. That much I know, because that's how it will deflect. Where exactly? So I should know the distance either from the left hand or the right hand. Right hand sounds more easy to calculate because your triangular loading is this way. So let's do that. By the way, the slope will look like this. This is not necessary for you to draw, but if you draw it very good, you'll get the slope here 2 times the slope here. Now let's take a free body with X bar. Okay, we don't know how much X bar is, but for sure X bar will be such that this load that you get on your conjugate beam must be balanced by the reaction at that support B, M naught L by 6 EI. So very easy, the area of this triangle must be equal to this. Finished. So easy. You do that, the area of the triangle is half this ordinate into X bar, and when you do that, by the way, you have to do it little carefully, because how do you get this ordinate? This ordinate you get from similar triangles, because when you draw a triangle at X, let's take X measured from the right hand, X, when X is equal to L, this is the ordinate. So X at some intermediate point X bar by similar triangles, you will say X bar by L times this ordinate. That is the intensity of the loading here. Remember with our discussion in the last lecture, it has units of kilonewton per meter. Look at the variation. When X bar is 0, it's 0, and it's linearly varying to this quantity. So you have to first derive this. You can derive this from this by similar triangles. Then you get this area, which is this into half, and then equate this to this. You do that, you get X bar equal to L by root 3. So that's exactly where the deflection will be maximum, and you plug into that and get the value of M bar, M tilde. M tilde will give you delta max. You go through this exercise, you'll get the answer. Of course, you could write it like this. So instead of root 3, you can substitute and write it as a decimal. Doesn't matter. So this is the exact answer. The deflection variation will look like that, and that's the answer. Now we'll take a slightly difficult problem, which direct integration method will also not be so easy to do. Moment area method, you won't be able to do it easily. Let's see how easy this is to do by the conjugate beam method. This is a propped cantilever with an internal hinge, the child-parent story that we discussed earlier. The question is very simple. What's the deflection at C and D? And we'll also find the slopes at C. Slopes at C, I said, not slope at C, because at C you can have two slopes, one on the left and one on the right. It's a very interesting problem. Sorry. So first we have to analyze this problem. If you do the child-parent analogy, then you know that this 20 kilonewton, we've done this earlier, I think last class. 20 kilonewton is shared 10, 10, and this 10 goes here, and very easily you can find VA and MA. VA is 10, MA is 40. Okay, so that's known. With that, you can draw the bending moment diagram. We did this in the last class. So you've got the bending moment diagram. Now you need a conjugate beam, and you have to load that conjugate beam with this diagram divided by EI, the curvature diagram. The conjugate beam should be drawn in such a way that the fixed end becomes free, the simple support remains a simple support, hinged or roller, and the internal hinge becomes an intermediate support. So this will be a beam with an overhang. Very interesting. A beam with an overhang. Incidentally, it works the other way also. If this was your real beam, this would have been your conjugate beam. Okay, so you've got a beam with an overhang which you can handle. On this beam, you will apply this loading, and it's got a funny loading. Part of it is negative, part of it is positive. You do that. Negative will point downward, Q will be downward, positive will be upward. Very interesting. Mind you, it's an imaginary condition. And you have the values. This 40 you divide by EI, this 20 you divide by EI. EI strictly will have the units of kilonewton meter squared. So that 40 divided by 40 kilonewton meter divided by kilonewton per meter squared will have the unit of 1 by meter, which is the unit of curvature. Okay, you've got this. Now what do? Well, find your support reactions. Well, to do that, take the total load of this triangle, which is the area of the triangle, 40 into the span 4 divided by 2, 80 by EI is the total area of this triangle, and the total area of this is 20 into 4 divided by 2, 40. So these block arrows are just the resultant loads applied. This is pointing up, this is pointing down, this is located at a distance span by 3. We know that. This is in the middle. With this information, you can get your two support reactions. We can do a little calculation. If you take moments about C, you can get RB. Let's do that. So you'll find that this into this distance gives me an anti-clockwise moment. Okay. So this distance is 2/3 of 4, and with respect to so this gives me anti-clockwise, and this gives me, if I take moments about C, this also gives me anti-clockwise, right? That area is 40 by EI, and that distance is L by 2, that's 4 by 2, and RB plus into 4 is also anti-clockwise. So everything is anti-clockwise, which tells me that RB will turn out to be negative, and I got some answer. Okay. RC is easy to get once I've got RB. Why? Total load minus this, and if I solve that, I get 113.3 EI. So I've got basic information for me to proceed. First, I want to know the deflections at C and D. The deflection at C and D are nothing but the bending moments at C and D in this conjugate beam. By the way, the deflected shape looked like this, and I can, if I want the slopes, I'm getting the slopes also. This slope at B is given by this reaction here. And here you have to be a little careful because the slope here on the left need not be equal to the slope. In fact, it won't be equal to the slope at right because you've got an internal hinge which allows you change in rotation between the left end and right end, but the deflections have to be the same. This slope is easy to calculate because it's nothing but the same area. And the fact that you've got a minus sign shows that it's going to point like this, a tangent will point like that. This you can get by the relationship, the difference between these two with the proper sign. If you want, you can get this slope, if you want. But the question doesn't ask for the slopes, the question asks for deflections. To get the deflection at C in the real beam, I need the bending moment here, which is simply 80 by EI into 2/3 of 4. That's all I have to show. And it's going to point downward, so that's a negative sign straight away. If I want the deflection at D, it's a bending moment at D. So I have the support reaction, very easy to find out. You can calculate, draw your free body and calculate your answer. So that's it. You should put a modulus sign and give delta C, delta D. No method can be faster than this method. No method. That's the power of the conjugate beam method. And I wish this is now introduced as a replacement for moment area method for civil engineering students in third semester itself. It's easy to follow up after you teach bending moment diagram. So you can substitute. EI is given as 4 into 10 raised to 4 kilonewton meter squared. Why is it kilonewton meter squared? Because E has a unit of Newton per millimeter squared or kilonewton per meter squared, and I is millimeter raised to 4 or meter raised to 4. So EI is always kilonewton per meter squared. And your final answers, if you get in meters, you have to convert to millimeters and you get 5.33 and 3. These are numbers which are realistic. Real beams will deflect only so much. That's why you don't see them. Okay, here's an interesting problem where you have a changing EI. This is a stepped beam. It's a non-prismatic beam, but fortunately, you could have a tapered section, making it more complicated, but we have a stepped section. So one half of the beam has an EI which is 2 times the other half. Does it mean the depth is 2 times? No, not necessary. If the cross section is rectangular, I goes up with the cube of the depth. So you need not have the depth 2 times to get this. So we are given this expression. We know that if the whole beam had one uniform depth, if it was prismatic and the flexural rigidity was EI, we've already solved this problem. The maximum deflection here is PL cubed by 3EI. And the slope here will be PL by 2EI. PL squared by 2EI. How will those numbers change if I stiffen one half of the beam? That's a simple question. Well, you can do it easily by the conjugate beam method. First, okay, the questions asked are delta max, theta max. Draw the bending moment diagram. The bending moment diagram does not depend on whether the beam is prismatic or not because the problem is statically determinate. Here's a question, chat question for you. The bending moment diagram is linear. Will the curvature diagram look the same? Till now all the problems we did, the shape of the bending moment diagram, shape of curvature diagram, which is the loading diagram on your conjugate beam, was identical. Will it be different now? Or will it be the same? The shape will be one triangle or will it be different? I want an answer. Same or different? If different, what's the difference? What will be the shape looking like? You have to type either same or different. Till now all the problems, the bending moment diagram looked exactly like the curvature diagram. Or the other way, curvature diagram look. One will be trapezoid and other triangle, different, perfect answer from NMIMS. Perfect answer, well done. You guys know this subject very well. So what do you have to do? First, draw the conjugate beam. The fixed end becomes free, the free end becomes fixed. All you need to do is to take this diagram, take every ordinate in it and divide it by the corresponding EI. So if you take this triangle on the right side, EI is constant, you will get a perfect triangle like this. But at this junction, the same bending moment will produce two different curvatures, one on the left, one on the right. Because on the right side, rights mean infinitesimally to the right, 1 nanomillimeter to the right. What will happen? 1 nanometer to the right. You are going to divide by EI. On the left, you are going to divide by 2 EI. So you get a step here in the loading. You actually get the step there in the loading. The curvature, local changes in curvature are not, you cannot see with the naked eye. Because it's like change in moment. But deflections won't change like that. Only curvatures change like that. Okay, so that's all. This arrow becomes halved on this side, and the right side, this PL you have to divide by 2 EI. So this will have the same height as this. That's the story. So you're right, this is a trapezoid and this is a triangle. So what? You don't care. You get what you get and it's easy to find your support reaction. Moment you get your support reaction in your conjugate beam, you've got the answers. You've got your maximum theta and delta. So find the resultant load. So this is where those formulas might help you. Or you break it up into rectangle and triangle and do it very easy. Do it whichever way you want. A1 plus A2 is the total area. Let's do it. A1 is the area of a triangle. Ordinate here is PL by 2I. Length is L by 2. And half that will give you my area. I get some answer. A2, I'm going to break it up into two parts. I don't want to use that formula, but if I can use the ready-made formula. So I'll take a rectangle and a triangle. The rectangle is PL by 4 EI into L by 2, and the triangle is half. Okay, this is done in a very simple way. It's just the average height. This height is PL by 2 EI, this height is PL by 4 EI, and the average height is half of that. That's very easy to do. Into L by 2. So you got this answer. So theta max, you've got the answer. Finished. Now delta. For delta, you need the centroidal distance. That's where, if you want, the first one is very easy because this is a triangle, so this divides this region in the ratio 1:2. That's easy. But the second one, you have to do carefully. You can use the formula I've given you in the table, or you have to work it out. I think here the formula turns out to be this. That's it. You apply that and you get your answer. So this is the change that happens. You need to compare it with the answer that you get had the whole thing been EI. So you just compare this. Instead of PL squared by 2 EI, you have 2 EI would have meant instead of 5 you got 8 by 16. Instead of PL cubed by 3 EI, you got 17 by, instead of 1 by 3 you got 17 by. That's it. Always compare because you know intuitively that the deflection is going to be less because you're stiffening the beam. It can't be more. Good. Now we'll do something very, very interesting. Maybe we're a little ahead of the time of Third semester normally you don't teach all this. Fifth semester also they may not know. Seventh they'll know. But you can use the same conjugate beam method to solve even indeterminate problems. Remember the fixed beam became free. So let's see how that works. We've got, let's look at simple fixed beams with symmetrical loading. So I've got a fixed beam, fixed at A, fixed at B, meaning no slope, no rotation, constant load W. First let's understand the meaning of this. Well, I've got support reactions W by 2 and W by 2, and I've got some moment which I call a fixed end moment, MF. Here it will be symmetrically in the other direction. MF causes hogging. I don't know the value. Actually there are two more support reactions which normally I don't draw. There is a horizontal reaction, but that makes the problem more indeterminate. When you draw bending moment and shear force diagram, that horizontal reaction does not cause any effect. So we can ignore that for the time being and worry only about drawing shear force and bending moment diagrams. Okay. So it's easy to understand it this way. This is going to be a deflected shape. The slope here is going to be 0, the deflection here is going to be 0. So normally it will sag and now it will hog. Supposing this was simply supported, it would have deflected by WL cube by 48 EI. This fixity is going to reduce that deflection. How much will it reduce? Let us see. Well, you could make your life easy by going back to the simply supported beam and saying that whatever I get here is a superposition of the effects caused by the external load W and these redundant moments MF. Okay, this is how statically indeterminate beams are understood. This will make it go down, this will make it hog and go up. And the net deflection here is this minus this. We know that. But the real problem, I may not even be interested in the deflection. I want to draw the bending moment diagram. I can't draw the diagram unless I know MF. And I'm showing that you can use conjugate beam method itself to get MF. How do you do that? Well, due to the first part, the triangular loading, you get a bending moment diagram like this. You know the maximum value there is WL by 4. Due to the hogging moment MF, you get a constant moment like this. This is minus hogging, this is plus sagging. The net thing can be drawn like this, right? And you can actually put your beam line exactly there. This is your net moment diagram. In the middle region, sagging, you can match this diagram with the deflected shape. This is your bending moment diagram. Your points of contraflexure where there's a change from hogging to sagging, sagging to hogging. Got it? Only question is, I know this value is WL by 4. I don't know what MF is. How do I find out? Let's look at the conjugate beam method. What's a conjugate beam for a fixed beam? It's a free beam hanging out there, subject to self-equilibrating loads. The loading caused by the sagging and the loading caused by the hogging curvatures. Very easy to understand. So the bottom part I know is WL by 4 EI in the middle and it's linearly varying. Top part I don't know, but I know it's MF and it's constant divided by EI. So imagine I have something floating in the air, forces pushing it from below and forces pushing it from above, and it's self-equilibrating, which means the total load acting upward, very easy, area of this triangle, half WL by 4 by EI into L, that's WL squared by 8 EI, must be balanced by the total load acting downward, which is MFL by EI. Equate those two and they must have exactly the same line of action. You've got a formula. You've cracked the problem. It's no longer statically indeterminate, become determinate. MF is WL by 8. Okay. MF is WL by 8. There's another way to look at it, and it's a very powerful way. if these two have to balance, you could even argue that MF is nothing but the average value of your sagging bending moment diagram. Why? Because MF is this divided by L. So it's the average value. If I draw the average of this, and that's going to give me my MF. That's another way to look at it. If the beam is subject to any symmetric diagram, loading, you'll get this. So we've cracked this. We can go one step further and calculate the deflection also. How do we do that? Take the same problem. Now we know the answer, WL by 8. That's the deflected, maximum deflection in the middle. Conjugate beam is free. Those are my loads. I know the deflection maximum at the middle. So, and the slope there is 0 because these two are going to be exactly equal. This value is my maximum deflection. And if I work it out, you'll find that this load from below into 1/3 this distance minus this load into half that distance. If I do a little calculation, I get the answer straight away. WL cubed by 192 EI. I want to compare this with the answer that I get in a simply supported beam. And you will find that in a simply supported beam, it is WL cubed by 48 EI. 48 EI is 4 by 192, I think. Whereas this is 1 by 192. So the fixity actually reduces my sagging moment to 25%. That means 75% is lifted up because of the hogging. That's a very interesting point to note. The easier way to do it is look at it from the deflection from this point. I know this answer, WL cubed by 48 EI. I know this answer, MF L squared by 8 EI. I find the difference and get the same. So there are many ways of solving these problems. The deflection for fixed beam subjected to concentrated load is 4 times less. Not 4 times less, is 3 times less. Isn't it? 1/4 is less. Is it 4 times less? 1/4 means 3 times less. Okay. Now we'll take a UDL, find the maximum deflection of the fixed beam. But before we get the deflection, we must solve the problem. Draw the bending moment diagram and find the maximum deflection should be the question. Okay. So, can you tell me, chat question, can you tell me what is the formula for MF? I'll give you a clue. Draw your simply supported beam with the same loading. You get a parabola with a maximum value of Q0 L squared by 8. So what will be MF? I want an answer. It will be the area of, you fill in the blanks. Let me have the answer quickly. What is the fixed end moment for a fixed beam subjected to a uniformly distributed? I've got an answer, Q L squared by 12. Perfect answer, well done. So what you need to do is take the average value of your parabola and you'll find that the area of the parabola is 2/3 the area of a rectangle, so 2/3 of this. That turns out to be, and the average value of that. That means divide that by L, you get Q0 L squared by 12. That's the answer. Well done. What about deflection? The deflection can be easily obtained, delta 1 minus delta 2. Delta 1, we already know, we've done this before, 5 by 384 Q0 L raised to 4 by EI. The effect of the hogging moment is mf L squared by 8EI, subtract the 2, plug in the value of mf is q naught L squared by 12, and you will get an answer 1 by 384. That means the original deflection reduces to 1/5, 20%. Earlier 25%, now 20%. The previous question was not clear. Let's see what she was trying to, whoever asked that question, is what happens if W moves from the middle? If it's unsymmetric, we'll come to that. Your question is a good question. It'll need extra calculation. Time is running short, but we'll at least show you how to do it. Okay, it's wait. We'll crack that problem also. First, we'll do the easy ones. First, we know how to crawl. Then we'll learn to walk. Then we'll learn to run. And hopefully someday you'll learn to fly. Answer to your question. What happens if it's unsymmetric? Don't worry. Every problem has a solution. What do? First, break it up into a simple problem. Okay, simply supported beam subjected to the unsymmetric loading. Plus you have fixed end moments. Now because of lack of symmetry, the fixed end moment at A won't be equal and opposite to the fixed end moment at B. So we give it a different name. We say MFAB and MFBA, but we are pretty sure both will be hogging. So this will be anti-clockwise, this will be clockwise. But we've got two unknowns now. How do you crack this problem? Well, draw the bending moment diagrams. Due to each of them, due to the loading, you'll get some shape. Okay? Depends on the loading. And due to your fixed end moments, you'll get something, but it's not going to be uniform like we did earlier. MFAB and MFBA, one of them will be larger than the other, or maybe equal in a rare case. Then, when you superpose, it might look like that. Well, whatever be the diagrams, they will balance one another, and you need two equations to crack MFAB and MFBA. What are the two equations? Well, firstly, this is a free beam. It's hanging out there. It's self-equilibrating. So, first the areas must match. This top area must be equal to the bottom area. You must know how to calculate areas. Trapezium easy to calculate. This will depend on the loading. They must match. Not only they must match, moment equilibrium should be satisfied. The lines of action must also coincide exactly. You've got two equations. Now, let's do the problem that you wanted me to do. You wanted me to shift the load away from the middle. I did that. I anticipated your question. I've got an answer. How do you solve this problem? Easy. MFAB, MFBA. The reflected shape might be like that. Okay, this should not give you the impression that the maximum deflection is under the load. No, it will be in between the load and the middle. Conjugate beam, free. This diagram I know, the maximum moment whenever I have a load like this will be WAB by L. Why? Because the reaction due to W in a simply supported beam will be W into B by L, and this is W into A by L. That into this distance will be WAB by L. So this is WAB by L. Curvature means I divided by EI. And on top, okay, I can guess this load is nearer to the left, so this moment is likely to be more than this moment, so I drew it like this. Also, I know the centroid of this is going to push the CG away from the middle to the left. So you got it. This has got to be balanced. This area is the area of the triangle. So the ordinate is there, the span is there. I can multiply and get the area. This area is also the area of the trapezium, average height into span. I've got these two. That's one equation. Okay, I'm ready. Not enough. I need one more equation. Okay, so this simple equation tells me the relationship MFAB plus MFBA is equal to WAB by L. Not enough. I need one more. That I get by measuring this centroidal distance C for both of them. I do that. And you know, I've shown you this formula. If I get a triangle like this, C is given by A plus L by 3. So I've got this C. This I can get from a trapezium. I can prove this. Then I equate that. I've got my answer. MFBA is WA squared B by L squared. MFAB is WAB squared by L squared. Problem solved. If you want, you can calculate deflection. I leave it to you. I want to end by saying that this can be applied to any problem where there are two unknowns. So you could apply it even to a propped cantilever that is fixed at A and not fixed at B, allowed to roll at B. How do you solve this problem? Well, you have only fixed end moment, MFAB. This B is not fixed. The deflected shape is likely to look something like that. The slope at A is 0. Conjugate beam is a funny beam. The earlier one was also funny, it was free. Now it is free hinged or roller, whichever you can put hinged if you want. You might say this is unstable, it's something is wrong. Nothing is wrong. You are not going to build these beams. Don't ever build such beams. But you can imagine such beams. This is not a real beam. This is a conjugate beam. This is the real beam. The real beam should be stable. The imaginary beam need not be stable, can be self-equilibrating. You're looking only at statics here. Here you're looking at both statics and kinematics. So stability is important here, not important here. Okay. Now what's the loading on this beam? The loading on this beam is the curvature diagram that you get from the bending moment diagram divided by EI. Now we can draw the full bending moment diagram, but that is messy. So we'll draw it in two parts. First, the diagram caused in the simply supported beam, the sagging moment diagram, which we all know is going to be like this, WL by 4. Then the hogging moment diagram will now look like this, because you have only one fixed end moment here and 0 fixed end moment here. These two now must self-equilibrate. Got it? That information is enough for you to solve the problem. But I want to ask you, will this area be equal to this area? Is that the meaning of self-equilibrating? It doesn't look equal, no? Will the bottom area be equal to the top area? Yes or no? And if no, why not? Next question. This area may not be equal to this area, or will it be equal to area? If it's not equal, what is that difference equal to? Not equal, is that? Why not equal? What will be the difference in areas equal to? At least tell me that. Bottom area will be maybe more. What is that difference equal to? Difference is equal to the reaction in the support. Perfect answer. Well done. Because you will have a reaction here also, and that actually will give you the slope at B. Very interesting. But so you can do that. It should be marked there. There will be a reaction there. That's the slope at B. You equate these two, you've got your answer. And then you can solve the problem. Okay. So broadly I've covered this topic. You can do hundreds of problems if you want, but the concept is important to understand deeply, to enjoy, to relish. This is normally not covered in textbooks this way. Something new, something worth knowing, and you'll be comfortable dealing with fixed beam subject to any loading, propped cantilever subject to any loading. You can have even two-span continuous beam. You can handle all these problems. Okay. So I want to sum up with bringing you to the big picture. We covered a small module. The module was flexure in beams. So the type of structure we looked at was a beam. But in reality, beams don't exist in isolation. They are part of big structures, maybe frame structures. So in general, if we come back to the original context, we are trying to do structural analysis. Structural analysis is actually the application of structural mechanics to predict the response of a given structure when it is subjected to given loads. Normally, we worry about loads that are obtained due to gravity or due to wind or earthquake or soil pressures or live loads in bridges and buildings. But loads need not be caused by forces and moments alone. Loads can also occur due to support settlements, it's called indirect loading, due to constructional errors, due to temperature effects, etc. We should be able to do all that. So we must be able to model the structure, and usually in structural analysis the elements are such that the cross-sectional dimensions are very small compared to the length. So we take line elements with a skeletal structure, and the real challenge is to predict the response of a given structure when it's subject to loads. The structure should be modeled correctly, and the loads, as I mentioned, could be having direct actions or indirect loading. And what is the response? Well, response are of two kinds: force response and displacement response. If your structure is a beam, then the force response is made up of your support reactions and your internal forces, which are bending moments and shear force. At any section, at all sections, you capture them by drawing the shear force diagram and the bending moment diagram. And there's a displacement response, which means deflections, slopes, curvatures. The curvatures must be matchable to the bending moments. So you should know the big picture. This is what we need to do. The structure itself is made up of various elements connected by, at the extreme ends or intermediate locations, by supports, and you could have joints, rigid joints, hinge joints, etc. That idealization has to be done. The elements could be a space frame or a plane frame element, a grid element or a beam element, a spatial truss element, a plane truss element. We looked at only the beam, but actually you should learn all this, and you will do so provided you understand it in a simple way, the way we have done the beam. And the joints can be rigid or pinned or semi-rigid, and the supports can be fixed or guided fixed or hinged or roller or elastic. These are the spring supports. You must learn in this manner. And you should know at what level you have to do your analysis. So first you have to worry about whether the structure is, of course the structure has to be stable. If it's unstable, you won't get a response to a loading. It will cave in. And if it is stable, you want to use it, you have to decide whether the structure can be analyzed. So it's indeterminate or determinate. We've already looked at static determinacy and indeterminacy, which is in terms of forces. So if your structure is said to be statically determinate, if you can get all the forces by simply applying equations of equilibrium, which is called statics. But if there's another approach. You look at the displacement at the joints in the structure, and the degrees of freedom, independent degrees of freedom, add up to what is called the degree of kinematic indeterminacy. A fixed beam, for example, is kinematically determinate. The joints don't move. So this is from the displacement approach. So you have two types of determinacy. We looked at static determinacy, but there's also kinematic indeterminacy, and most problems in practice, multi-story buildings for example, are both highly indeterminate statically and kinematically, and you have two approaches. One is called the force approach, where you look at static indeterminacy, also called the flexibility method, and the displacement approach or the stiffness method if you look at kinematic indeterminacy. Then you have to see whether the problem is linear or non-linear, whether it's static or dynamic, whether it's deterministic or probabilistic. So if you're a real ustad in structural analysis, which I hope you will be, some of you, when you specialize in this domain, you should be able to do non-linear, dynamic, probabilistic analysis. That's at a research level. If you can do that, Deterministic is a special case of probabilistic. Static is a special case of dynamic. Linear is a special case of nonlinear. At undergraduate level, BTech level, we expect you to really know how to do linear, static, deterministic analysis. First, of simple statically determinate structures like beams, and also of statically indeterminate structures. I suggest you take a look at this book which I wrote some years ago. It's called Structural Analysis. I've already mentioned it's published in India by Narosa. It's divided into 5 parts. The first part is fundamental. The second part talks of force response in statically determinate structures. The third part talks of displacement response in statically indeterminate structures. There are many methods to find the displacement. Conjugate beam method is only for beams. You can't use it for trusses. You can't use it for frames. So there are beautiful methods. The best method is by applying the principle of virtual work. And this is covered here. After doing this, we are ready to do statically indeterminate structures, force methods, and then we look at the alternative kinematically indeterminate structures, displacement methods. Some of these topics are covered in NPTEL video lectures where I did a course on advanced structural analysis. There's a book on advanced structural analysis, which is matrix methods of analysis. But the first 10 lectures out of those 42 lectures cover the basics of structural analysis. If there are no questions, I assume you understood what has been covered, but there will be some questions later. My suggestion is go through these videos again, go through your class notes again. You are most welcome to write to me through email. My email ID is given on the first slide. But I suggest you discuss among yourselves and you talk to your class teachers. This is a very beautiful subject. You need to learn it and to enjoy it. Okay? Thank you. Goodbye.